So back in 1969, hidden forces inside the moon threw Neil Armstrong, like 8 kilometers off his landing target. And today, NASA's actually facing that exact same invisible threat.
Yeah, it's pretty wild. I mean, a modern Artemis lander has a terrifying 1 in 30 chance of failing entirely because of it.
Right. So welcome to a new deep dive. Today we are looking at this incredibly fascinating report by Timothy J. Dillon from 206 Innovation, Inc. And it's all about something called curvature variable physics, or CVP.
Exactly. And our mission for you listening today is to really understand why NASA's current lunar descent math is basically breaking down, and how this radical new framework turns that 1 in 30 gamble into absolute mathematical certainty.
Yeah, because to understand the solution, we first have to look at why orbiting the moon is so historically dangerous, right?
Right. I mean, current Artemis mission designs treat lunar gravity like it's smooth and perfectly uniform. They just assume the gravity field is this even, predictable pull all the way down to the surface.
Okay, let's unpack this. So NASA is calculating a landing as if they're approaching a perfectly smooth billiard ball. But the moon's gravity is actually, more like a lumpy potato.
That is a great way to visualize it, honestly, because high-resolution data proves the moon is just littered with what we call mascons.
Mascons.
Right. Yeah, mass concentrations. They are massive, dense concentrations of rock hidden right under the crust, and they create these severe, very localized gravity spikes.
Oh, wow. And the report calls this geometric blindness, right? Like,
Yeah.
if your navigation math ignores these lumps, you get pushed off course.
Exactly. It's exactly what pushed Apollo 11 so far off course, and it literally destroys satellites.
Yeah, like the Apollo 16 PFS-2 satellite. That was supposed to orbit for a year and a half.
Yeah.
But those hidden mascons yanked its orbit completely apart. It crashed in just 35 days.
35 days. It's incredible. And this lumpy gravity, well, it isn't just an orbital annoyance. It triggers a literal mathematical crisis right before touchdown.
Wait, how close to touchdown are we talking?
In the final 15 kilometers of descent, the lander hits these unmodeled gravity gradients. So basically, the computer experiences sudden, intense gravitational pulls it just isn't expecting at all.
Which causes the math to just blow up. Like, the report calls it unbounded mathematical divergence. The guidance equations literally can't solve themselves anymore.
Right, and what's fascinating here is the so what of it all. This geometric entropy literally pushes the lander into chaos.
Because the computer starts firing thrusters to fight these ghost forces.
Like, don't understand, right?
Pushing terminal velocity errors past 12 meters per second.
Exactly. It actively prevents the craft from reaching the landing site. Because of this, the Artemis baseline fails to converge in 100% of tested simulations.
Wait, hold on. Let me challenge that for a second. If the math literally breaks down into chaos 15 kilometers above the surface, how do we ever safely touch down? Like, how did Armstrong survive?
Well, Armstrong famously had to take manual control. He had to visually fly the module out of that chaotic computer guidance just to find a safe spot.
Oh, I see. But for today's autonomous missions, you don't have a human to hit manual override.
Precisely. You have to completely rewrite the math. Enter curvature variable physics, or CVP. Instead of fighting these gravity anomalies, CVP makes curvature a dynamic variable.
Here's where it gets really interesting to me. It applies these 88 omega theorems, which the report maps to the famous Collatz conjecture.
Yeah, the Collatz conjecture is this famous math rule where no matter what random number you start with, the rule always funnels you down to the exact same sequence.
Right. It loops to 1, 2, and 4. Always.
Always. So CVP uses that principle. It filters those chaotic gravity forces. The target landing zone literally becomes a universal attractor, just like that 1-2-4 Collatz cycle.
So it acts like a funnel. Instead of fighting the gravity bumps, the math uses them to spiral the lander perfectly to the target. And the velocity errors drop from 12 meters per second down to under 0.3.
Under 0.3. But if we connect this to the bigger picture, running dynamically shifting equations like that in real time requires immense power.
Yeah, standard flight computer would just freeze up instantly.
Exactly. You need NVIDIA Edge AI running directly on the craft to crunch it all without lagging.
And since places like the Shackleton crater have that severe high-frequency radio interference, you have to wrap the whole AI system in a geodesic shield.
Right, to protect the calculations locally. You can't just rely on a signal from Earth.
Wow. So taking all this together, we've explored how dynamic curvature math and the 88 omega theorems attempt to save Artemis from terminal divergence.
It really is brilliant, taking that lumpy potato physics and mathematically guaranteeing a totally smooth ride.
Absolutely. Which leaves you with an incredible thought to ponder. If treating gravity as a computationally intensive dynamic variable perfectly solves lunar landings, what other impossible space missions across the solar system might suddenly become achievable?